Alright, so we are back with another tutorial on the simulated 6502 microprocessor. And this time, if you have been following along, you may notice a bit of a difference on our workspace here. Most obviously, we now have an old CRT monitor here. And it's just showing black, but you can kind of even see there's a little bit of a reflection in it. And not only that, our processor info's moved over here. It's kind of covering the trash can a little bit. But we've also added two more panels. One of them, a memory monitor, whatever that means, and also some display info, which seems to show some colors associated with some hex numbers. And so you might have guessed it already. What we're going to be doing today is filling the entire display this time with color, and we're also going to be changing the color, so repeatedly filling the display with different colors. And that's going to represent a huge step up in complexity from our last program, which just filled the display from right to left, just one little line of color here. So one of the first things that we want to be aware of is this memory monitor on the desk here. And you can see it's showing a whole ton of zeros right now. But interestingly, we have like some line numbers here telling us what piece of the memory it's showing. And each of these line numbers is actually showing us basically 16 numbers across corresponds with 10 hex. And so this basically goes up by tens and then obviously by like A, B, C, D, E, F. And this is showing a piece of our RAM right now. It's showing our RAM from position 00 up through position FF, or 255 is the very end of our RAM right here. And what we can actually do is if we wanted to like show some different spots, we could maybe show like, say we wanted to show what would be the stack of the computer, which you don't need to worry about what that means right now. But the stack is like from 100 up to 200, I believe, or 1FF maybe. And now when we put each of these in, you can see it's showing us some different rows in here, right? And so these are allowed to be bigger than 1 byte numbers that we can put into these little slots for our memory monitor, and that lets us show any position in the computer's memory, at least any position that it can read. There's certain things like, say we went to the display itself, maybe we might not actually be able to read what's in the memory right then. We can only put stuff out on the display with pixels. But that's what our memory monitor is, and it's going to be pretty useful to us at some point here. And the other thing we want to highlight here is this display info. And you'll notice something, it's a little bit different from the last tutorial where our display was like right up here. Our display info shows 0, 1, but then it also shows like 16 different colors here, all from 0 all the way up through F, which is 15. So 0 to 15 is 16 different colors. And that means that we're actually able to display like a wide range of colors, or maybe even an image if we put that into the EEPROM on our little screen right here. And so that's what we're going to be doing. But just to demonstrate how this works, let's start off with a simple program that just puts one of these colors in one pixel on our display. And that will get us back up to speed from where we were previously. So you might remember from before, our display is a memory device, and it starts at address 5000 hex, which is 20,480 in decimal. And our display from before was actually 64 pixels wide. I've bumped it down to 32 pixels for this just because of the amount of time that it takes to fill the display, time in terms of clock cycles. And right now I'm still kind of pushing the boundaries of what this simulation is able to run. But basically, our clock ticks at about 100 times a second. It might be closer to like 90 times a second because we have a 90 frames per second headset, and so it's limited to 1 tick per frame max, except that we then run a for loop every time that tick goes off, and we can have that do like 100 clock cycles or even like 500 or 1,000 clock cycles in order to try and reach a kind of similar speed to the actual 6502. So you will notice later in this tutorial, it takes a while to fill the screen, and I'll probably be taking a second to go back to my computer out of VR to speed up the clock a little bit in order to demonstrate this to you concisely. However, this does lower the frame rate of the headset, and I'm definitely still working on optimizations for getting the simulation to run faster. But in the meantime, let's get started with our display. We all know, as we just discussed, that our display starts at 5,000 and it's a 32 by 32 display, which is a little bit smaller than before, as we just discussed. But if we did 32 times 32, we would get 1,024 decimal. And if you wanted to try and guess at the hex, go ahead, but it turns out it's 400 hex. So that means that our display goes from address 5,000 hex to 5,400 hex, or 21,504 in decimals. So, if we want to simply put a pixel on the display, color a pixel on the display just in that top left corner though, this isn't going to be very difficult at all, and we're really just going to need to put something in address 5,000. And we've already done that plenty of times before. So maybe let's pick out a color that we want to use here, and we can load it into our A register. So, we have our load A command right here, A9, load A immediate. That's the little hashtag. And that'll just load in whatever value we give it. So I kind of like the color E right here. Kind of like this dark color. This is based on like a Windows 95 or Windows 2000 color palette. So let's put, or maybe Windows 98. It's one of the early 16 color palettes used in like icons in the file system, the shell, all of that sort of thing. So let's get out our E color. And so this number, because it's 0E, is representing that color E right there. And so if we put this into our program, we can now, if we say we uploaded this to the EEPROM, reset the computer, and ticked once, we get A9, that's our opcode. And then a second time, there's our operand low is 0E, and now our A register has 0E in it. Great. So now let's finish out our program because we need to be able to store it to our display. And that's going to involve a store A command, and we're going to use 8D right here, which is store A absolute. And so an absolute command takes it's a 2 byte address, so 16-bit memory address to store our value to. And you'll notice right here our reset vector and our IRQ vector, both of those are in little endian format, and that's how every 16-bit address is represented on the 6502. So what this means is our reset vector, remember that from earlier tutorials, that our EEPROM right there starts at address hex 8000 or 32768 decimal. Well, in little endian format, we put the 00 in 8000 after or before the 80. And so then this more significant byte is what it's called. The most significant byte comes after the least significant byte. So that's something to keep in mind here. But if we just want to store something to 5,000, well, we can make a number with 00, and we can make a number with 50 hex, obviously. And there we go. Now, if we were to like rearrange these, boom, that would be 5,000. We'd be storing our thing out to the display right there. And that's kind of what we want, but we just have to remember to have it in little endian format. So let's put in that 8D 00 50, and if we upload this to the EEPROM, reset our computer, we tick it twice, you see we have our A90E as our opcode and operand, and then we tick it again, this time we get 8D, that's our store A, 8D, right? And then operand low and operand high. So we need to tick 2 more times to get both of those. So here's our operand low is 00, and our operand high is 50. Great. So at this point, you can see one pixel on our screen is now lit up in that E color, which it's pretty cool actually. So that's the basis of writing to this 32 by 32 screen. And at this point, we kind of want to get started, I'm sure, with the actual program. So I'm actually going to clear out our program here so that we can kind of get started with this. So one of the first things to keep in mind here is with a range from hex 5000 to hex 5400, that's like your 1024 different pixels. That's a lot more than 255 pixels, which is 255, that's the biggest number that we can store in 1 byte, right? So FF 255 is what fits in 1 byte right here. So what we actually are going to need is a 16-bit counter. So you remember from the last tutorial when we filled up the display from right to left, we went down here and we used decrement X, I bet, CA. And what this would do is we would set our X register to be like it was a 64 by 64 display, so I believe it would be like hex 40. Yeah. So we would like set our X register to 40 and then decrement X until it reached 0. Well, we're not able to do that this time because this only works on 1 byte. So what would happen then if we decremented it past that? Well, it would probably roll around, I think. And so that wouldn't really be an ideal scenario. So what we need is some way to carry our counter between 2 bytes. That way we have a 16-bit counter. And while we're at it, since we do have a 16-bit counter, we might as well just count up from our top left corner and fill up the display like that until we get to the bottom, and then come back up to there. All right, so in order to get started with this, we're going to need to load some things into our register. So I'm going to get out some load A commands. Need to throw that one away. There we go. Grab the right ones this time. Because there's going to be a couple of steps in our program here. There's going to be a bit of an initialization step where we set up these counters and get them ready. Having the initial values and everything in them. And then there's going to be another set, which I would kind of consider like the loop or like the bulk of the program. And the loop right here is going to store our value and then increment the counters and then check if we need to come back to the beginning or anything like that. And then at the very end, there will be a little bit of extra logic in there just to handle changing the colors between each of these 16. And then also when it reaches F, changing it back to 0, like resetting it back to 0. But the reason that I got out these load A instructions right here, both of these A9s, is because we're going to need to initialize things to begin with, right? So where do we want to start counting from? We know that this pixel that we just stored was at address 5000, so maybe that's a good place to start, right? Let's do that. Let's start by getting out some like 5000 hex right here. And you can see we're going to be doing things in little endian format again. But something maybe to keep in mind here is our A register is going to be changing as we go through this program. We can't just have our register dedicated to storing where we want to be writing out our pixels to, right? So we're actually going to need the memory for this, and you might have kind of seen this coming with our memory monitor here. But we're going to actually be storing these values from the A register actually into what's called the 0 page of the memory. And this right here from 00 to FF is the 0 page. And the reason that we have an advantage with the 0 page can be demonstrated if I get out a couple of these little commands right here. Let's go into our load menu just so that we can see just any of these. And let's compare 8D to 85. So we just used opcode 8D to store something to 5000. Remember, so we had 0050. as our 8D store A absolute command. Notice how when I was doing that, I ticked the clock 1, 2, 3 times to get it there. You can see we're at like 8004. It took us 5 clock cycles, 2 to load and then 3 to put it out on the memory. And that's fine, honestly, because we were just doing that once. We put it out there. That works all right. But if we wanted to be like accessing values in memory like really quickly, we don't actually need to use like this full address. And so what the 0 page is maybe say I got out I don't know, let's say like 42 hex here. Put that down here. The 0 page is named like this because you see our more significant byte of the number is always 0 on this 0 page, right? It's 0000, 0010, 00F0. So each of these, and you're not paying attention to the right-hand side, I hope, just to that left, the more significant byte. That's always 0. And so what our 0 page commands do is they basically have an implied 00 in our address that we're talking about. And so in this way, it's only going to take us 2 clock cycles to store something into the memory of the 0 page as opposed to 3 clock cycles. And yes, technically we could actually put in like our 00 or 4200 right there, and that would, our absolute thing would still store it into our 0 page, but that's a waste of a valuable clock cycle, right? So what we're going to be doing here is actually storing our A9s. We've loaded these into our A register. We're actually going to store them out to the 0 page, and our memory in the 0 page is going to keep track of where we want it. Basically, it's going to keep track of like a pointer for which pixel we want to be storing a value to next. And the reason that we have to store this in the memory is because we're also going to eventually have some arithmetic logic here, like add with carry with our 0 page. And that's going to be how we handle the 16-bit numbers that we have here. Because, like this is now a 16-bit address that we're trying to represent through using multiple bytes. All right, so I feel like it is finally time to start putting things into our program and putting that together, right? So the first thing that we need to do is store our value 00, our beginning least significant byte, into our 0 page somewhere. And so let's find a store a 0 page command. Well, I have one right here. And let's store that in the 00 position. So what's going to happen now is when we run this program, it's going to put 00 right in there, in that first slot of our 0 page, which that will work just fine for us. If I were to run the program right now, you wouldn't see much because it's already 0, but we can't assume that that's going to happen. Because say your computer got hit by like some radiation, maybe from the sun, or what if your computer's working in space, right, where there's a ton more radiation that could flip any of the bits in these bytes. We can't really assume that it's going to be 00. So we always have to store stuff like 00 to our memory just to be sure. But then our second one is going to be just storing out 50 to our 0 page. And let's come back up here to load and get another one of these store a 0 pages. And we're going to store this one in address 1 this time. My bad, kind of dropped it into the wrong spot right there. I need to actually reset where my center point on here is because I'm running into my dresser. Just a second. All right, great. So we've reset our view and I can now reach all the way through there. Perfect. Okay. So were I to run this program now, which, why don't we? Let's upload it to the EEPROM and reset our computer. You'll notice that the pixel goes away, unfortunately. Goodbye, little E pixel. But now if we run this, we have A900, right? And so our A register is now initialized to 0. And then 8500. So what it's doing now at this point is storing what's in our A register, which is 0, 0, out to position 0, 0 in our memory. Then we're going to repeat that for the value 50 hex and store it in position 1 in the memory. So 1, 2 gets us 50 in the A register. And then 2 more clock cycles gets us 85. So store a 0 page, and then our upper and low of 1. So that stores it into the first position in our memory. And look at that now. You can see we have 0050 stored in the memory. So that's great. We've kind of accomplished what we wanted to with this bit of the initialization, right? But we're also going to need to talk about a couple of other issues here. And one of them is, well, what do we do with these values in our memory, right? Like now we have them in RAM, but how is that going to help us put stuff out on our display, right? Well, I think we need to store one more value before we get started with this, and that's going to be the color. And you'll see how that becomes important as well here in just a minute, I guess. So in order to store a color, we're just going to once again, we're going to get out an A9 opcode right here. We can put it directly in, and we want to load color number 1 in because our display seems to be initialized to color 0, right? Or black. So let's get a color 1, and then let's also store that to the 0 page. So we need another 85 command. Is someone in my room? Someone is in my room. All right. So if we scroll down a little bit here, we need to think about where we're going to store this. I feel like the best place to put it is just the next position. So this is position 2 because 0, 1, 2, right? So let's get out a 2. And now we can also have our color stored in the 0 page. And that way we can, I guess, increment the color whenever it's time to do that. And color we can luckily increment easily by using one of these increment commands. And I bet one of these here, increment 0 page, this is E6. I bet we'll be using that a little bit later in the program because that will increment one of our memory values right here. And then every time we go to place a pixel, we can just load that value into the A register from our 0 page. Okay. So at this point, let's keep going with our program, I guess. We need to talk about how we're going to use these memory values that we've put in the 0 page, this 0050, to get an address that we can store stuff to, right? And what we're going to do, and I'm just going to tell it to you and then explain it after, is what's called indirect addressing. So maybe let's come over here and go back to our loads, right? We're going to be doing a store A, and it's going to be indirect. So I believe it's going to be this opcode 91 right here. Although I should probably just check my notes to be safe, right? I can see in here that we're storing it with 910. Okay, great. So this opcode 91, which I just verified is what we actually want to be using, you'll notice it has this kind of strange addressing mode, which is like in parentheses ZP for 0 page, comma Y. And so the parentheses mean it's an indirect addressing mode. And what that's going to do for us is whenever we have a value in our 0 page, such as these values right here, 0050, we're actually able to use these values in combination with what's in the Y register to get a actual memory address to store stuff to. And so when we evaluate this opcode, it first looks in whatever we give it as our operand. So we're going to be using 00 as our operand, right? Because our address starts at 00. You see? So 00, we have the value 00. And then in 00 plus 1, so 1, we have the value 50. So it reads these two values, and you gave it the first memory position to read in the 0 page, and then it takes the second memory position automatically, puts them together, and gets an address. but then that address is also added to, or what that address is also added by whatever is in the Y register at the time. And so what we actually need to do here is set our Y register to be 0 as well. Because if we set our Y register to be like 1, for example, when we ran this, it would put these together, so it would get 0050, it would be like, oh, it's 5,000 hex, right? And then it would add 1 to that because 1 was in the Y register, and it would be storing our value out to 5001. So just to be safe, just in case like some bits have been flipped or we don't know how the processor was initialized before, we definitely need to store 0 into our Y register. And if we were to be messing with the Y register in our program, we should probably also set our Y register before we do any storing of values using this command. We should probably set it back to 0. But I'm pretty sure that we're not going to use the Y register in here other than at the very beginning to initialize it, so we're probably safe to have it in this initialization here. So in that case, we do need a load Y command, and that's probably going to be somewhere right around here, right? There's load A hashtag. Here we go, A0, load Y, immediate. We're going to throw a 00 into there. And now that's all set up for how we are going to actually, I guess, interface with these values in memory to get an actual position, like a 16-bit memory position out of them. So at this point, I guess we're probably good to begin with our loop, right? Because we have all of our stuff initialized, we might as well start trying to write some stuff out to the screen, huh? So the first thing we need to do is figure out what color we're going to be using. Well, remember that writing something to the display is just a matter of loading a color into our A register and then storing our A register. And this is the storing part. So we just need to be able to load A from our memory position 2, which is what we saved our color to and what will be changing whenever our color changes. So let's come around here and find a load AZP command. Load AZP. Looks like A5 is what we're going to be using. And we can really just put this right into our program, it seems. And we need to specify an address to be getting that from. And our color is stored in location 2 in our memory. So let's get that out. We're going to need a 2 hex. Perfect. And put that in. So now, at the beginning of our loop, we will have our A register set up. Basically, our A register will be set to the value that we want to be our color. And one thing here, this is the start of our loop, right? With this A5 command, and because we're going to want to be jumping back to it later, I think it's probably worthy to get out some numbers just to help us remember right now what positions these are in memory, because right now the program editor does not have like any sort of index for you to see where stuff is in memory. And we can't just like count the rows easily because sometimes we have like a 3-byte command. Sometimes it's only 2. And so at some point I'll implement like a nice little counter that shows you like what memory position things are at. But in the meantime, let's just count these up, right? So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. A, B, C, D, E. So this is at 8,000 and E. I'm just going to put that off to the side right here so that we can remember that's where our loop begins. And I'm going to take a drink of water right now because I've been talking for a minute. And the next thing that we need to do in our loop is simply store out our value that we just loaded into the A register, except we need to store it in this special way that we've already discussed. And the special way is using the indirect addressing mode. So let's put in these two as well. And so now we've taken care of basically all of our memory locations, right? First, we've used our second memory location right here, this memory location 2, to load up what color we want to have written out to the display. And then this one is using memory location 0, and then it automatically looks in memory location 1 as well to get that value. So we're really done actually with like the storing a pixel part of our loop. And I feel like maybe if we ran this program, it might put out a pixel, but I'm not entirely sure. So, well, you know what? Let's give it a try right now and see. So I upload to the EEPROM, make sure that that's clicked, and reset our computer. Now, let's come back up to here, right? First 4 instructions are just going to be putting 0 in right there. So 1, 2, 3, 4. So 0 has been saved out to memory location 0. Then our next 4 are going to be storing 50 to memory location 1. So 1, 2, 3, 4 ticks. And now 50 has been stored to memory location 1. And then finally we have, right here, we're going to be storing 1. This is all new stuff down here now. We're going to be storing the value 1 into memory location 2. So 1, 2 ticks to get 1 in the A register. 2 more ticks then to store it out. And you can see we now have 1 right here in our memory location 2. And now at this point, we load 0 into Y just to be sure that our Y indexed indirect, or maybe indirect Y indexed, is going to function properly. Basically, that it won't be offset by the Y register at all. So our Y register is now set to 0. And then finally, we can load into the A register the value from our 0 page. So 1, 2. Now our A register has been loaded with this value in 2. So this 1 from position 2 is now in the A register. And then finally, we're going to take 2 more clock cycles to hopefully store this out to our first pixel. And let's see if that works. 1, 2. And look at that. We now have a nice white pixel in the corner of our screen. And it's white because we have 1 stored in that color value in our memory, right? Okay, great. So I would say that so far our program seems to be working as intended. So I'm going to scroll down a little bit here. And at this point, it's probably time to begin working on our address counting because we want to increase our address as we go, right? A bit more sparkling water here. All right. So at this point, we are going to be making our 16-bit counter, and this is really like the star of the show in this program. It's what enables it all to work correctly. So, in order to build a 16-bit counter, we're going to be using in here add with carry with the 0 page, and that seems to be this opcode 65. And maybe if we went over that for a second, like exactly what this does, that would give you a better understanding of how this counter is going to work. So, our add with carry. When I program this into the simulation, add with carry simply adds to the accumulator. So remember, the accumulator is our A register. It adds the operand to the accumulator, and then it tacks on the carry flag if it's set. Okay, so let's break that down. First, we have our accumulator. Right now, it appears to be 1. That may or may not be what it is when we actually run this program. It might not be 1 exactly, but pretend we were going to be doing... I actually don't want this one for demonstration purposes because it's using our 0 page. We're actually going to want 69. Nice. Let's get out like a value like 5 right here. So, ignoring this one for a minute, I'm going to hide it under our table here. So we have 1 in, and I'm just using the values that are already here for clarity. We already have 1 in the accumulator, right? Well, we're going to add to the accumulator what our operand is. And so we add 5 to 1 and we will get 6. So the accumulator will then become 6. But this little C part of this is carry. And do you see here how we have these flags? This is a register. It's an 8-bit register holding flags. And right here, this last flag, the carry flag, gets set in some different scenarios. But one of the times that it gets set is if this overflows 1 byte. So say we had honestly, say we had FF, right? Already in the A register. Pretend A is FF, right? Boom, there's our A. And then we added 5 more to it. Well, now there's a problem, isn't there? So our A register will not be showing actually the addition of 5 and FF, not in the way that you or I think of it. But it'll be showing like what's kind of looped around back to 0. And then the carry flag gets turned on because we're basically carrying over to the next bit. And so what happens is if we got out a second one of these, pretend we're now like going for this second time, well, first it adds into here our carry flag. And that way we can handle 16-bit stuff, because if you imagine like our 8th bit of a number, let's come over here and do some binary stuff for a minute. This is 3, 6. I think I need one more. There we go. Okay, so 0, 1, 2, 3, 4, 5, 6, 7. So what we would number as the 8th bit, or the computer's 7th bit if we start with 0 counting, that value, if you imagine this being added into another like string of binary numbers, another byte over here, this would go into the lowest value right there if we carried it in, right? This is just like when you're adding something. When you're adding 2 numbers and like the ones place overflows, then it goes into the tens place, right? So this is basically the same idea here. So let's clear that out, okay. And what this means is we can implement a 16-bit counter by using the carry flag from the least significant byte. Okay, and so whenever that least significant byte overflows 255, we just increment the more significant byte using this because it brings in our carry flag. And that way we can have a counter that can count up to like 65,535, or FFFF, 2 bytes. There you go. So that's basically the upshot of this. And what we're going to do here is kind of swap out our 69 instruction for 65 here. And the difference between these two is obviously in the addressing mode. And I was using the immediate one to demonstrate this to you because it makes more sense. It's the number that's right there. But this 0-page addressing mode version right here just gets our number from the operand in the 0 page. Okay, so let's throw some of these away now, and we're going to get started building this counter. So our value in the 0 page that we want to be adding to is value 0, 0, right? So we're definitely going to want one of those right there. And in order to increment that value by 1, we're probably going to need to have 1 in our accumulator already. So let's get out A9 and get a 1 in there. Great. So now whenever we run this, it will add. Now, one thing to keep in mind here is if our carry flag's been affected before this, it would count and it would mess up our instructions. So we actually also need to clear the carry flag before we do any of this. So we're going to come down to flags here. And 18 is clear carry. And you'll see the addressing mode is I for implied. That just means that you don't have any operands along with it. I'm going to go back to showing all of these for a second. So now we know for sure that the carry flag is going to be 0, so it's not going to add that. So all we're doing here in this like little chunk is adding 1 to whatever the value in our 0 page is. And technically, it's adding the value in the 0 page to 1 in the A register, because all of this happens in the A register. And then we need to actually store that back out to our 0 page. That way, it gets saved, right? And so in order to do that, we're going to need an 85 command, store a 0 page, and it's going to be stored into the 0 position in there. And so this is all the code that we need for that lower byte of our 16-bit counter. And while I'm right here, I'm just going to check on my notes and make sure that I've done that right. We have 85, 0, 18. Okay, yeah, perfect. I so far have not made any mistakes, thankfully, in recording this video, but it might take a couple of takes. Anyway, we can put all of these into our program here. And it's very easy when we've already thought out exactly how it's going to work, right? Perfect. So if I scroll up, at this point, we're now able to add 1 to this 0 index value in our 0-page memory. However, we currently are not doing anything with a carry that might show up. So say we get like, this is a 32 by 32 display, say we get like around here somewhere is going to be where it rolls over, that 255 rolls over, right? Whenever that carry comes on, nothing's going to happen right now. And so we're not actually accomplishing anything. But at this point, we might as well have just used like incrementing the 0-page position that we talked about earlier. But we are now going to write the code to implement that. So I'm going to scroll a little bit, but keep in mind that we've already like cleared the carry flag and loaded 1, that sort of thing. And we're just going to be worried about what happens with our carry flag now. So what we want to happen is we don't want every time we go through this loop to be incrementing our more significant byte, because that would be increasing our thing by like 100 hex or 256 decimal. We don't want to be jumping by 256 every time, no. We only want to increase this if the carry is on. So what we're actually going to do is be load a 0 first. And that way, assuming that nothing here, where's our where is the value that we need? There we go. 65 again. Perfect. So that's actually going to go below right here, and we're going to need a load a instruction. There we go. So what's going to be happening here is we're going to load 0 into A so that by default nothing is added, and stuff will only be added if the carry flag is on, and otherwise it'll just add whatever's in the 0-page address to 0 or itself, right? So maybe not the most efficient thing here. If we could maybe optimize it, but honestly it might take the same number of clock cycles anyway, and this computer handles everything in 1 clock cycle for every command, so I don't know, it's probably about equal either way, but obviously if you have other suggestions on how to do something like this, try implementing them yourself and sharing a video of doing that, right? So at this point, we need to add our like 1 index value in our memory, so we just get out a 1 here. And I just got a notification that my Quest 2's battery is low, so we're going to be plugging this thing in, so just a second. While I take care of that, you can tell that this recording is going wonderfully right now. I'm actually pretty happy with it so far. Could have been a little more clear a couple of times, but it's going okay. Alrighty then. So we are plugged back in as far as I can tell. I should actually check the color on the side. Yes, okay. Alright, we're charging. Perfect. So, with this all set up, basically, it's going to add, like in the scenario that it's in right now, it's just going to add 50 to itself, right? And so, yeah, that's not really the most interesting thing or the most efficient, but it is what it is, and it makes it not terribly difficult to implement this 16-bit counter. So we just need to store this out now. You see we have like 85 right here. Let's show all. It's going to be kind of over here somewhere, right? 85? Guess I better go in our load thing and go looking. There it is. Accidentally pulled out a store Y as well. But we're going to store that back to position 1. And so the only case that position 1 in our 0 page will have been changed is if that carry flag was on. So let's put all of this into our program now as well. Cool. So now our counter works. But one thing you might notice if you've been paying some attention is it's not like gonna go back to the beginning or anything when we do that. So, that's all right, but it probably could be better, right? So, and just a second, my Airlink is like acting up really badly. I might actually have to pause this recording or something because, yeah. What do I do? Okay, I'm just gonna pause the OBS recording for a second while I fix Airlink. So, starting the recording back up after maybe 5 minutes here. I think that I fixed my Airlink, and I just copied out our program to the EEPROM, saved that, and then put it back in. So I think if I load from EEPROM, we should be right back to where we were before. And we are. Perfect. Okay. So after that brief intermission to fix stupid Oculus issues, we can get back to what we were doing, which was going back to the beginning of the loop is what I was talking about, because at some points in our program, we have to return back up to the start of the loop so that we can either keep going to fill the next pixel or go back like really far to the beginning by resetting stuff and then filling the pixels again. So yeah, there's definitely some uses for returning to where we were before. Okie dokie then. So we were having some issues with Airlink for actually the second time in a row here, but it is once again corrected. So, what was I talking about? All right, so after correcting these Airlink issues, there are definitely some cases where we want to be able to return back to a certain point in our program as we were talking about before. And what that means is we either need to be jumping somewhere by default, like this would be like a 20 go to 10 sort of thing, where we, no matter what, when we hit this jump instruction, we go back to the beginning. Or a branch instruction, which is what kind of like lets us implement some logic into our simulation of filling this display. And so if we go in logic here, actually not in logic, control is where we want to be, or branch. So here's our branch instructions. You'll notice we have all of these that are like branch if equal, branch not equal, branch carry set, branch carry clear, branch overflow set, overflow clear, that sort of thing. So in this case, we want to be going back to the beginning of our loop, which is right up here. Where is it here? Here it is. So it's at A502, which, if you remember, I had saved 800E as just a number right here to remember that as the beginning of the loop, but in resetting Unity a couple of times, that obviously went away. So we want to be branching back to that 800E if it is not time to be doing anything else special. And the reason that I phrase it like this is because we're going to be using this D0 command, branch if not equal. And it's a relative command, which kind of involves branching with a offset as opposed to a specific position. So if we went in here to like control and we got out jump, which we will need later, but this jump instruction acts differently in that it's an absolute position. So it just sets the program counter to a certain position and lets it keep going. Whereas the branch if not equal, it actually calculates the position to branch to based on your operand and the program counter. So we're going to have to do a little bit of math to figure out how many spots we need to go back to get back to 800E, right? And right now we have a bit of a bug here where whenever we change our mode here, I think. Like whenever we drag these, it only it highlights in our program which ones each of these are. Like if we go to load, you see it highlights the load. But it's all right. So branch not equal. So we're going to be branching back to the beginning of our loop if what is not equal. Well, we're going to have to do some comparisons here. And the comparison that we want to make is to see if our display is full. And remember, our display is 400 long and starts at 5,000. So we want to be seeing if we are going to be like touching 5,400, right? And we have a really great way of doing that, actually. Remember that our program stores our low order our low order byte of our 16-bit address in the 0 position. It stores the high order byte in the 1 position, and it stores our color in the 2 position. So we can actually compare our value in our 2 or in our 1 position, that is the high order byte, to 54. Because if it's 54, we don't care what this one is, but we know that we've gone to the very end of the display. Like, whatever value this is, if this was like 03 or something, we'd be like past the display, kind of, back into like more address space, kind of, that's not hooked up to anything really. So we can compare stuff to 54 in order to decide if we need to be branching or not. And in order to do this, we have this command right here, C5. And that's comparing our 0 page. So what does that mean exactly? Well, we are comparing the value in our 0 page given by the operand. So we're going to obviously want this to be 1 because the 1 index position here in the 0 page of our memory is going to be 54 when we reach the end of our loop. We're going to be comparing that to the A register again. So we obviously need yet another load A command. I feel like A9 might be like the most used thing here. And so if what this comparison does, and the reason that this comparison is this like kind of more bluish green color if we went down here, the reason that it's in the arithmetic section is actually because it's kind of just subtracting. So what it does is it just subtracts our values here, and it subtracts the value in our A register and the value from our 0 page. And if there's 0, well, it's going to turn on this 0 flag right here. And so the branch if not equal command then looks at the 0 flag, and it branches if the 0 flag isn't on. Because if you imagine like 3 minus 3, 3 and 3 are the same because 3 minus 3 equals 0 is basically what we're saying, right? So in this case, it's checking to see if the 0 flag is on, well then you gotta keep going. But if the 0 flag isn't on, or these aren't equal, then we branch and we get back to where we were before. So we can probably put these into our program. However, there's definitely going to be a bit of like a process that we're gonna have to use here to handle what we are what we're going to be jumping back to, right? So for now, let's just put these into our thing, and I might have to check my notes here to make sure that I'm doing things right again. And I'm also bumping my finger into, or my controller into my bookshelf again, because that would be its own position. 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B. So we're at B at A9. C, D, E, F. Okay, so we're at 0F now. Now it's going to be 1, 0, so 10, 11, 12, 13, 14, 15, 16 maybe? 16 or 17. I don't know if I kind of lost count or anything there. But what we need to do then is think about a way that we can represent this to the computer, because remember, we're jumping backwards, and that's going to be involving some negative numbers. And you know what that means? It's our good old friend, the 2's complement. So, 2's complement arithmetic. In order to get the 2's complement value of a number, you invert it and add 1. Okay? So, let's represent like a byte right here. Okay. There's our byte. It's 80. It shows on the thing. But that's 1000, or if we put this in decimal, say we put 80 in for decimal, it's 128. And if you remember anything about 2's complement, you'll remember that the number of values that 2's complement can represent is from positive 127 all the way through 0 and everything down to negative 128. Okay, so it can actually store one more negative number than positive number here. But right here, our 128 value, notice that that's one more than 127. That should be resulting in like a negative 128, or maybe a negative 1. I'm not entirely sure. But we go through the process in order to figure out what this is. So we had 1, 0, 0, 0, 0, 0, 0, 0. Okay, so to invert this, we're going to change that to a 0, right? And then we're going to add 1. So we change that one to a 0, change all of these to 1s because we basically invert the whole thing, and then we add 1 to it. So we're going to end up with 0, right? So that's the 0 is going to be our first thing that was a 1, right? And then 1, 1, 1. That's the like higher order. 1, 1, 1, 1. And this value then represents our our halfway point, right? We have inverted the number, but now we need to add 1 to it. And here, let me just show you with there we go, one more thing. So we need to add 1 to this number. Well, we add 1 right here. It's not going to become 2, I can tell you that. It's going to stay as or it's going to become 0 because 1 and 1 is going to be 0, but we carry the 1. And then 1 and 1 is 0, and we carry the 1. 0, carry the 1, carry the 1, carry the 1, carry the 1. We end up with, if we clear this out, 1, 0, 0, 0, 0, 0, 0, 0. 3, 4. And guess what? That is, oh dear. Wonder how that ended up right here. That's going to give us, again, 128. Or 80, except that this time we know from this calculation that it's representing a negative 80. And so if we were to represent our offset of like 17, I thought it was, something, hex 17 or something around there, in 2's complement, we can calculate that out, right? And so I have it written in my notes here so that we don't have to go through that all again, and it is E9 is where we're going to be going. So let's put that in and just kind of see what this looks like in binary. Okay. So, a couple of things to think about right here. First, we have a and I don't want to create it quite yet. First things first, our 7 index bit of the byte is 1. And in 2's complement, if that leftmost or the 7th bit is 1, then it means that it's a negative number, okay? And so what we could do is, if that thing is 1, we basically subtract 256 from this, is another way to think about the invert and add 1 thing. And so were we to do that, right, we go into decimal, 233 minus 256. That would give us the value that we need to jump to. So let's go in our calculator here, and I'm just looking at my phone through the tip of my nose. 233 minus 256 is negative 23. Appears to be what we're going back to, maybe? So, all right. Clearly that is how that's how we're going to represent this in 2's complement. And I probably should make a video on 2's complement to kind of explain that a little better, maybe with like a whiteboard or something like that, so I can show stuff not on just this calculator. But in the meantime, since we've calculated this all out, it's E9, and we're going to put that in there for our D0. And I also, once again, need to reset my view in here, or else I'm going to be touching the wall, which would not be good. And we need to reset it again, because it's, once again, in a bit of a funny spot. Okay, great. So now we're good. So E9, negative 23, I think is what it came out to. Maybe we should just, like, check that and see. So negative 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 21, or 20, 21, 22, 23. Okay, so yeah, we do seem to be moving back the right number of spaces. If this doesn't come out for some reason, we can always, at the very end of our program, go and check and see what happened. But, I'm kind of curious to see if this works, and if it doesn't, I'll probably end up editing it out, but let's upload it to the EEPROM and see exactly what goes on. So we reset the computer, right? Then we can tick it. 1, 2, 3, 4, 5, 6, 7, 8. We now have 50 in there. 9, 10. We now have 8, 9, 11, 12. Now we have 1 stored in there. So at this point, we are right up here. We still need to load 0 into our Y register, so 2 more ticks, and we get 0 in the Y register. 2 more ticks. We've loaded A based on what is in the 2 index of our 0 page. Then we're going to store it out to our screen. There we go. It is stored. Good. Now let's see here what goes on when we run this entire thing, right? So 1 tick clears our carry flag just in case. Another 2 ticks is loading 1 into our A register, and then adding that to whatever's in here. So 2 more ticks, our A register stays 1 because that was 0. And now we can store that out with our 85 command. 1, 2. And now look, we have 1 stored into here. We scroll down a little bit more. We load 0 into our A register. So it's 0 now. And we add that to whatever's in our second order, or our second thing in the 0 page. So it's going to be 0 plus 50, so our A register is still 50, and there was no carrying or anything going on, so we take 2 more ticks just to store that back. And then we come down here, A954, that's going to be loading 54 into our A register to compare with that, right? So 2 more ticks for the comparison, right? C501, that's giving us our comparison between this and 54. And what you'll notice here is our Z is definitely not on. Our Z is 0, because 54 and 50 are not the same. And so branch if not equal E9, it should take this branch. So you'll notice our program counter's at 8022, 8023 when it reads the D0, and then 8024 right here. But then it's going to be jumping all the way back, I believe, back up to here. Right, so somewhere right around here. Let's see what happens here. It says it's at 800D, which is interesting. I kind of feel like that should be 800E, so we might need to check on that as well. Let's tick it once and see what happens here. Oh, okay. So, yeah, that makes sense. I was being a little bit stupid because I had recently rewritten how this worked and forgot that the program counter ticks at the beginning now instead of at the end. So we're all good. It's reading A5 to load our color again. And then couple more ticks, takes 1 more here, and look at that, we have now put out our second thing onto the screen. So I'm actually going to pause for a second here, and we're going to speed up our clock slightly. Well, 100, okay, sure, that seems fine. I can run this for a second, but I don't want to like get it out of control to the point where I'd have to like restart Unity to fix this, because our program isn't really complete and we could maybe screw up something in the computer if we let it run too long. But say we ran the clock. Look at that. If this gets past 255, which it did, you see how this one moved up to 51 then, right? And pretty soon it'll even go up to 52 when that hits FF. You can see that our 16-bit counter is working wonderfully. And so I'm going to stop the clock. And if we look right here when I pause this thing again, just to show you, right here, let me make sure you can see this in OBS the way I have it. Yeah, okay. So I shake the mouse a little. Right here, this min clock time, our clock delay is at 0.1. So every 10th of a second, it seems, it's incrementing. And then every 10th of a second, it runs like a for loop to tick the clock 100 times. And so that's how we get this like insane speed that's able to fill this display so quickly. You would not be using this speed for any of like the simple programs using just like port B or port A or something like that. But when you have like 1,000 pixels to iterate over, it makes sense to speed things up a lot. And this can reach a decent fraction of the actual computer's like 1 megahertz speed. So at this point, we have our first branch not equal all down. And before I like kind of rethought about this program when I was building it, I actually had a second one, but it turns out that that one was actually entirely unnecessary. So at this point, we're gonna reset the computer. Actually, I think that way we can get this thing back to 8000, and I'm gonna take a drink of water while I'm doing this and check my notes so I can see what I kind of want to talk about next to transition into the rest of the program for you guys. Because the rest of the program it's different than like this loop. It does a lot more like stuff that on one hand makes sense, you have to do it, but on the other hand, like maybe it's a little bit hard to see where some of it's coming from, right? So let's just think about the state that we're in right here when we have this branch not equal. So if it's not equal, basically if what's in our memory is not equal to 54, then it's gonna go back to the loop and keep going because we obviously haven't reached the end of the display. But say our zero flag turns on. If our zero flag turns on, because the 54 equaled what was in the memory, which meant that we had filled the entire display, then this thing is not going to branch because this is branching if it's not equal. So this won't branch, this will just continue on. And so what do we want to happen after this continues? Well, we definitely need to revert ourselves back to the beginning of our display, right? That seems like one of the main things that we need to do here, right? And so the way that we're going to do this, I guess, is we're going to be setting our 0 page values back to the beginning of the display. So that's going to involve a load A of, let me see here, like which order I do things, right? Resetting our 0 page counters. We want to load, yeah, okay, we want to load 0 in first and then the 54 after, sure. So basically what we're going to do, and this might not be the most efficient use of memory space, but I do not feel right now like both debugging a subroutine, like jump subroutine, return from subroutine, and also explaining that right now. So we're just going to copy the code basically from the beginning of our program. So you remember up here in the initialization, length of this program makes me want like a double up arrow kind of, page up, page down. But in the beginning of the program, remember we loaded 0 into our 0 of the 0 page, and then we loaded 50 into position 1 in the 0 page. And so we're going to be doing that same thing down here. There we go, that worked pretty well. So let's load 0 first. There we go. And then we need to store it in the 0 page, so we need an 85 command, and I have managed to grab 2 of the wrong commands here. Put those away. And so that one needs to go in 0, remember, because this one's the one that counts every time. So that's going to be 0, right? And then we repeat this process. So we repeat our load A, which got that one wrong again right there. We repeat our load A, except that this time we load 5,000 or 50, so that 50 and 0, 0 makes 5,000, and we store that into the first position of our 0 page. I'm kind of going through this a little bit quickly here because you remember how we did all of that and why at the beginning of the video. And so now, if we were to jump back to our loop, it would basically immediately just start filling the screen again, because it's set our memory back to there. No longer is it like not taking the branch; it's taking the branch every time, and so it's just looping over and over. But you wouldn't actually know. And the reason for that is we would still be we still have 1 in our second position in the 0 page, and so the color isn't going to be any different. And so you wouldn't actually be able to see it, even though the computer would be like spinning its wheels, right? So what we need to do here is actually handle how our color works. And we're going to check first, and this is part of the thing that you might say is like, this feels out of order, right? But you'll kind of see how this ends up working. We're first going to check if our color is F, because if our color is F, well, then we want to revert our color back to 0, so paint black onto the display again, and then start this process all over. So we're going to get out an F opcode. And remember, our compare compares stuff, like compares our 0 page right here with the A register. So we're also going to need a load A command from right over here. Perfect. And we're comparing which 0 page value, that's our operand, that's going to be 0 page value 2. And so if this compare is the same, so basically if the color is F, well then compare is going to turn on the 0 flag for us, right? Because it's subtracting and it'll subtract to 0, right? So we want to be able to handle what happens if basically if our 0 flag is there. And so in order to do that, we can use another one of these branch instructions. So we come down here, what do we have here? BPL, BMI, BVC, like overflow setter clear, carry setter clear. All the way down at the very bottom, we have F0, which is branch if equal. And so this is going to do the opposite of branch if not equal. And so basically, if our carry flag is set instead of not being set, so as long as our carry flag is set, then it will take the branch. And so this will take the branch not every time, so it won't be taking the branch by default. It'll be taking the branch only if we've already reached like the end of our 16 colors and it's time to go back to the beginning. And so we're going to put this into our program, but we have to keep in mind here that this command isn't going to be like quite done, because there's a little bit more to do after, like assuming that we don't take this branch. And if we don't take the branch, then we need to like basically change the color. But if we do take the branch, we need another spot in our program just a little bit farther down to handle like resetting the color, okay? So therefore, we're going to leave that empty, but we should have a note to ourselves that we need to fill in this operand, right? Or else our program definitely will not work. So let's scroll down a little bit and change like our state of mind again, right? This time, we are pretending that we didn't take the branch, okay? And so we didn't take the branch. That means that our color is not this light blue, and it is not time to be resetting our color yet. Instead, it's actually time to be incrementing our color. And so that's where we have this little opcode E6, which I'm pretty sure I alluded to earlier in this thing, saying that that's going to show up, right? But what this increment is going to do is it increments a memory location. It's incrementing the 0 page of our memory. And so if we put that in here, And which part of our memory represents our color? Well, it's the second one. Or not the second, it's the second index, basically, 2, because this is 0, 1, 2, that's our color. And so we're going to increment that value in memory. And so that way, when we return to our program the next time, instead of displaying 1, it's going to go and do 2 then, right? And then after that, it'll do 3. So it'll keep on counting up. And the reasoning behind putting this compare before this all then is so that we can get through all of our F color before it increments up to, I guess it would be 1, 0 then. And so that's just kind of why this feels maybe a little bit out of order. But say we've incremented our color, right? It's now time to go back to our loop. So this is one of those cases where no matter what, we need to get back to that loop. And so in this case, we're going to be using the jump instruction. This is jump absolute, it appears. And so jump absolute takes a full 16-bit memory address. And that is where we're going to see the little endian stuff coming up again, because we have 8, 0, and 0e. So that's this number right here, is where we want to be going back to, because remember, we stored that as like telling ourselves this is where our loop begins. So we put in 0e first because of the little endian, and then 80. And so all of this is now pretty good, because assuming we don't take our branch, then we will just continue right on, right? Just continuing on to incrementing the color, and then right after we increment the color, we go back to the beginning of the program. But we still haven't handled what happens if we do decide to take the branch because our color is F. So this shouldn't be particularly difficult. We simply need to load color 0 back into the second index of our 0 page. And so in order to do that, good old friend A9, and we're going to put in a 0 byte. And then storing into our 0 page, this 85 command will store into the 0 page, and it's in the 012 address, as we've definitely discussed a few times at this point. And that will reset our color, but now it's time to go back to our loop again, right? And when we're finished with this is actually the end of the program, because we are basically every case is handled at this point. There's no way for the program to like get stuck doing something out here. And so we're going to put in that same 0e right here and 80. And we don't have to worry right now about how like you see with show all, how like any of these branch instructions were relative with jump, because it jumps to the address no matter what. But one last thing before we give this a test is we still haven't figured out what we need to put in as our operand right here. And so remember, this is relative, which means that it's acting very similar to this relative thing. Luckily, this time, we don't have to talk about 2's complement, right? Because we actually want to jump ahead in our program a little bit. So all we have to do actually is just count up how far ahead we want to jump. So we're right here, right? So this would be 0. Then 1, 2, 3, 4, 5. And now at the next command, basically, it will jump ahead then. So let me just make sure I did that correctly. Yes, F05, perfect. So let's get out a 5 opcode or operand and put that in right there. And so now, assuming that our color is F, well, it's like, okay, so we're going to take the branch. We take the branch, it counts 1, 2, 3, 4, 5. It increments our it increments our program counter one more time, and that gets us the value right there. Perfect. So I'm pretty sure if we upload this to the EEPROM, it should work. But, if not, then there's some debugging to do. So let's give it a try. Reset. And I'm going to hit start clock on here, and we already saw how quickly this thing runs. However, I feel like it might be worth letting like our first page kind of get filled up, and then I can increase the speed of the clock afterward, assuming that it gets through the first page correctly. So you can see at this point we're already at like 52, 53 now, so only 255 more addresses to go. And then that thing's going to hit 54, and then it quickly switches back to 50, basically. And you can see we did now increment the color. That's part of the E6, so our color changed from 1 to 2, and so it's now writing out gray to the screen. And so this is going to happen for all 16, which I feel like is a little bit redundant to watch, so I'm just going to speed things up here. And it's going to make me very nauseous in VR right now because the frame rate's going to go down. However, the program will now run much faster. So you can see we're already on color number 4, then 5, 6, little bit of Christmas colors there, 7, 8, 9. A is now the dark blue, B, C, D, E, love that color, and F. And hopefully at the end of this, it does start drawing out black again, which we can see it does. And so therefore, our program is running correctly. We have made what I believe is a pretty impressive and kind of complex program, especially if you're a beginner here. It takes into account like some slightly more advanced concepts than just like loading and storing and looping with this 16-bit counter, and also like storing our color and using that. That's just another simple thing. We now know how to use the 0 page, and you can see we've only used up 3 memory spaces in the 0 page, so there's a lot more still available. But computers at the time took advantage of every byte of the 0 page that they could, and every byte of their limited, expensive RAM at the time as well. So that's pretty much it for this tutorial. I'm going to have some editing to do for sure, because definitely some issues in the middle with AirLink and all of that. But yeah, beyond that, I think we are pretty good to end the video here with this program functioning correctly. So thank you guys for watching. I'm pretty sure that this was a long video, so thanks for sticking with it as well. And with that, I guess I will see you in the next one.